Once again, returning to a previous video, here's our output of a linear regression, and we talked about r in the previous video, but what about r squared? R squared is actually taking the number r and squaring it. In this case, it turns out to be 0.605, and we're going to come back and we're going to look at what does that mean. So I'm going to write that up here. R squared is equal to 0.605. This number is known as, it's often just called r squared, or the coefficient of determination. The way that r squared is interpreted has to do with the difference between what are called deviations from the average y and the residuals, which we talked about before. So here's our foot length and height data. This line here represents the average height. So we can think of a deviation as the amount that each person differs from the average height. So some people are taller than average, some people are shorter than average, and so forth. If we were to add up all of the deviations, they would equal 0, because that's what an average does. It averages out. It's about half of those differences are above average and half of them are below average, and so when you add them all up, you just get 0. Now contrast that to residuals. Residuals is the amount that each y value varies from the y value predicted by the linear regression. So here are our residuals, and notice they're a lot smaller, because when we know something about a person's foot length, we know a little something about their height. In general, we notice that people with bigger feet tend to be taller. And so when we draw the line this way, we're accounting for some of that variation in height by looking at the variation in their foot length. Whereas here, we're not really paying any attention to their foot length at all. We're just looking at their height compared to the average height of a person. So just this says on here, just on your sheet, this graph shows how much the height of each individual varies from the average height of this group. This graph shows how much the height of each individual varies from the height predicted by the regression based on foot length. Notice that there is less variation in height among people with similar foot length than the variation in height overall. Okay. Now, how can what I want to do is quantify how much better my prediction is using foot length than it was just using average height. So for example, if I told you I'm going to randomly select a person in this class, guess their height, and what would you guess? Well, you might just guess sort of an average height, because you have no idea, you don't know anything about the person at all. But if I said I randomly select a person from the class and I tell you what their foot length is, then you would have a much better chance of estimating closer to their height. So that's kind of what the difference between these two graphs are. In order to quantify how much better your guess would be knowing the foot length than not knowing the foot length, we're going to do what we did before with the least squares regression line. We're going to square each of these values. That's not a very much good square. And look at all those areas and add up all the areas squared. So notice we're going to have a lot more big squares of areas here than we will over on the linear regression line side. So here is a table of showing what I did. Here's the foot length, here's the height. The deviations are each of the heights minus the average height. So that shows you all of the different deviations from the average height. The residual is each of the height minus the predicted height. In other words, if I put foot length into the equation, then that gives me a predicted height, and the difference between the two is my residuals. Then, on my calculator, I take the sum of the deviations squared minus the sum of the residuals squared. So that gives me the difference between those overall amounts of variation, and I divide it by the sum of the deviations squared. This might look to you like a percent error calculation. That's exactly what it is. I'm saying I'm taking the amount of error, the difference in the two, minus the sum of the deviations, and I'm saying that the percentage of the deviation that is removed by using the foot length as a basis for making my prediction is 60%. In other words, R squared tells me that 60% of the variation in height is based on the variation in foot length. Okay, so if I know the variation in foot length, that explains 60% of the variation in height. Now, does that explain everything? No, because there are people with big feet that are short and people with small feet that are tall, and there's all kinds of variations in between. So you still have a lot of variability because people are different. But there's a lot of the variability that has been removed. Over half of the variability in height can be explained by how big your foot is. So that's what R squared tells us. It's a very useful measurement tool, very useful piece of information. We talk a lot about it in statistics. So if you take AP Stats next year, you'll have a little leg up on the competition.